All right, class. So today in this lecture, we're gonna go over the products that you get when you use oxygen as the nucleophile in nucleophilic addictions of aldehydes and ketones. So let's start with water. So if I take a molecule of water and add it to an aldehyde or ketone, what you get is you get this molecule here where the carbon of the carbonyl is no longer double bound to a CO, double bound to an oxygen. It's singly bound to two alcohols. We call this molecule a hydrate or a gem diol or geminal diol. Um, in general, the equilibrium doesn't usually favor the formation of the hydrates, except for like very simple aldehydes like formic acid. This reaction is very slow unless you catalyze the reaction under acidic or basic conditions. So let's look at the base catalysis. So in the base catalysis, this is usually using something like aqueous sodium hydroxide. And so what happens here is the OH minus is going to be the nucleophile. So this is basic condition. So the O minus attacks the carbonyl carbon, pushing the electrons up onto the oxygen to make the alkoxide intermediate, which deprotonates a molecule of water to give you the gem diol or the hydrate and regenerates the base here. Under acidic conditions, what happens here is that the water is not nucleophilic enough to attack the carbonyl carbon. So what happens here is the oxygen of the ketone or aldehyde is going to be protonated. It's going to attack H+. That makes the oxonium, which is much more reactive. That allows the weak nucleophile water to attack the carbonyl carbon, pushing the electrons up onto the positively charged oxygen. That moves the oxonium from this oxygen to the oxygen that attacked. You then will get rid of the oxonium and regenerate the acid by a molecule of water by a proton transfer. So a molecule of water will remove the proton off from the electronegative oxygen, the more electronegative oxygen, to give you the hydrate or the gem diol. Now, it's important, in general, like I said, the formation of the hydrate isn't very favorable for most ketones and aldehydes. But the reason we go over it is because those two mechanisms that I went over, they are going to set the basis for a lot of the other mechanisms that we're going to see. So the basic mechanism of hydroxide adding to the carbonyl, the acidic mechanism of protonating the carbonyl and water adding to that, those are going to be the basis for a lot of these mechanisms that we're going to see. So when you start thinking about what the steps are, what the steps are in a mechanism, or what's happening mechanistically in these nucleophilic addition reactions, remember, under acidic conditions, a strong base cannot exist in that acidic environment. Under basic conditions, a strong acid cannot exist in that basic environment. So what that means is when you're under acidic conditions, you're usually either making neutral intermediates or positively charged intermediates. Under basic conditions, you're either making neutral intermediates or negatively charged intermediates. Now, if we just move a little bit, if we just make the oxygen nucleophile a little more complicated, so instead of water, let's say we move to reacting the aldehyde or ketone with an alcohol. We get a much different product. So in this case, what happens here is if I take a ketone or aldehyde and I react it with an alcohol, the alcohol will actually react twice with the alcohol to give you a molecule where the carbon is attached to two alkoxy groups. So when the carbon's attached to two alkoxy groups, we call that an acetal when the starting material is an aldehyde. We call this so when you start with a ketone though, and you do this addition, we call this a ketal. And notice that we have this, what's really important here is these reactions are almost always done under acidic catalysis or acid catalyst. So we have this acid catalyst. The most common acids that we use for this are either our para-toluene sulfonic acid. It's usually either written as TSOH or PTSA. These are the two shorthand abbreviations for para-toluene sulfonic acid, or sulfuric acid. So let's go over mechanistically how this works. And remember, we're under acidic conditions. So because we're under acidic conditions here, let's not really worry about what the exact identity of the acid is here. But whatever the acid is, you're going to protonate the carbonyl. That's going to make this carbon more electrophilic. So my oxygen of my alcohol, which is a weak nucleophile, that's going to attack the carbon of the protonated of the oxonium. That's going to make this intermediate here, where the oxonium has moved from this oxygen to this oxygen. So now we're going to make this molecule neutral by the conjugate base of whatever acid you use, removing the proton here. Now, we make this intermediate here, which is called a hemiacetal. This is usually very hard to isolate. So the reason it's called hemi is because it's called halfway. So notice that in a hemiacetal, the carbon is bound to an alcohol and an alkoxy group here. So now what we're going to, so notice this is the nucleophilic addition under acidic conditions. To get rid of this oxygen here, this alcohol here, the next set of steps can be characterized very much as an SN1 reaction. So in the SN1 reaction, we need to make this a good leaving group. So this oxygen is going to protonate from the acid. The oxygen attacks H+, kicking out the conjugate base. That makes the oxonium here. That will cause this to leave. This water leaving is facilitated by this oxygen pushing its electrons down. Remember, we've seen this type of movement before in the electrophilic aromatic substitutions where alkoxy groups are activating groups via resonance. This gives you this oxonium here, which is super reactive. This will then be attacked by another molecule of the alcohol to give you another oxonium intermediate, but the oxonium is just now on a different oxygen. And then we regenerate our acid. So the conjugate base is going to remove the hydrogen from this positively charged, formal positively charged oxygen to give you the acetal. So overall, to get from here to the hemiacetal or hemiketal, that is the acid-catalyzed nucleophilic addition. And then to get from the hemiacetal to the acetal, that is an SN1 mechanism. Now, in general, like I said, for most simple aldehydes, the acetal can be favored. So for things like formaldehyde, if I react that with 2 molecules of ethanol in the presence of acid, I can get the acetal to be favored. The formation of the ketal, though, is not very favored. And again, that's because this is the ketone's not as reactive. Also, when you try to make this ketal here, like this looks like there's a lot of stuff attached to that carbon. That's a pretty sterically hindered carbon there. Now, one way we can make acetals and ketals more readily is by using the diol, or by using diols. And if I use a diol that's connected by 2 carbons as shown here, you can also use diols that are connected by 3 carbons. So if I use this diol, you get a similar looking product, but instead of the 5-membered ring here, what you would end up with is a 6-membered ring here. Making the acetals and ketals with the diol is usually much easier than using 2 non-connected alcohols. And the reason is because the moment you do the nucleophilic addition under acidic conditions with one of the alcohols, you end up with this hemiacetal or hemiketal intermediate. Now, if the rest of the steps are SN1, that's fine. And what you've actually done is because the nucleophile is actually attached to, so it's like an intramolecular SN1 reaction. And most of the time when the reactions are intramolecular, those reactions are much faster than the intermolecular reactions. Now keep in mind that this whole process is, and also, you can use the cyclic acetal, or you can use diols to favor the formation of the acetal or ketal. But also keep in mind that you can use Le Chatelier's principle to help form acetals and ketals. So for example, because a byproduct in this process here is water, if I can remove the water here, I can favor the formation of this. So Le Chatelier's principle says if I remove a product, the equilibrium is going to, the reaction is going to push the reaction toward the product side to reestablish equilibrium, right? So usually in order to favor acetal and ketal formation, you use a desiccant to remove the molecule of water that you form here that pushes the reaction over this way. Also, if you use an excess of the alcohol, right? So if I have an excess of the reagent, that's going to push the reaction this way. Now, once you make the acetal or ketal, we can actually convert this back to the starting aldehyde or ketone by using Le Chatelier's principle again. Because the byproduct of this is water, if I add a bunch of water on this side, that's going to push the reaction back the opposite way. And the mechanism of going from here to here are the exact opposite arrows that I showed you earlier. Okay? Now, one thing that you might be wondering, like, why am I going this way and then this way? Like, why do I want to be able to go around and around and around? It's not a weird merry-go-round. The reason you want to be able to do that is because once you make the acetal or ketal, this carbonyl carbon is no longer electrophilic to nucleophilic additions of Grignard reagents or hydrides. So you can mask this carbonyl here. And the reason that becomes useful is, let's say you're trying to make this molecule here, starting from this dicarbonyl compound. You have a ketone and you have an ester. And you want to try to just reduce the ester in the presence of the ketone. We know esters are less reactive, and in order to reduce the ester, I'd have to use something like LAH. Now, if I use LAH, though, that LAH is also going to reduce the ketone. So what you have to do to solve this is you have to mask the ketone in the presence of the ester. And you can do that because the ketone is more reactive than the ester. I can use this diol as a protecting group to protect the ketone. Once I do that, that makes this carbon not nucleophilic, or sorry, not electrophilic to hydride. So I can take this molecule here and react it with LAH, H minus, to give you the reduced product here, followed by an acid workup. That's going to protonate the alkoxide you make from here and also remove the protecting group there. Now, I want to revisit the hemiacetal very quickly. So remember I told you that when you go from the aldehyde or ketone to the acetal or ketal, you go through this hemiacetal intermediate. And as I said before, these are usually hard to isolate. One of the exceptions to the hemiacetal being not easier to isolate is when you make cyclic hemiacetals. So for example, let's say you take a molecule, a ketone like this, under acidic conditions. This oxygen is 1, 2, 3, 4, 5, 6. Anytime there's an oxygen intramolecularly, an oxygen that's 5 or 6 away from a ketone or an aldehyde, this cyclic hemiacetal or cyclic hemiketal are usually pretty favored. This is also really important from a biological standpoint because carbohydrates are essentially cyclic hemiacetals. So this is called the pyranose form. So this oxygen 1, 2, 3, 4, 5, 6, that cyclizes down to make a 6-membered ring, cyclic hemiacetal. Now this is called the pyranose. You can also make what we call furanoses, which are 5-membered rings. So in that case, it would be 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5. This oxygen would attack the carbonyl here to make a cyclic hemiacetal in the 5-membered ring. This is like the backbone. This is like ribose, right? The backbone that you find in RNA and DNA. So those are the products you can make from oxygen nucleophiles. So we talked about hydrates, acetals, ketals, hemiacetals, and hemiketals, and went over the mechanisms of how all of those things are formed. Thanks for listening, and let me know if you have any questions.